Okay, so we've just introduced the differentiation of a vector valued function and just summarized the differentiation rules that we have. Now let's see how we can use these rules to prove some things. So for example, we're asked to show that for a differentiable vector function r of t that has constant length, then the tangent vector is always orthogonal to the position vector. Let's think about what that says as an example. So as an example, maybe we've got our vector function, which is, we'll say cos of t, sine of t, and 0. So this is a circle in the xy plane. Okay. Is this vector valued function of constant length? Well, if I take the magnitude of r of t, that's cos squared t plus sine squared t square rooted, which is cos squared plus sine squared is 1, square root of 1 is 1. So yeah, it's of length 1. So this vector valued function is of constant length, and so this result says that the tangent vector is always going to be perpendicular to the position vector. Let's see if we believe that. So here's our curve that's given by that vector valued function. That's r of t. So these are the set of all points whose position vectors are given by r of t for various values of t. Let's pick an arbitrary point on there for some t value. If I draw the tangent vector, that's the tangent vector, r prime of t. Here's the position vector of that point, that's r of t, and they are right angles to each other. Now, just by looking at this, I'm sort of, intuition's telling me that, yeah, it looks like they're right angles. The tangent vector to a circle is perpendicular to the radial line connecting the center of the circle to that point. That's what this result is actually saying in general. It says the circle is only a special case of this kind of curve, a curve which is of constant length, a curve which is given by a vector valued function of constant length. It says no matter what curve you have, if it's of constant length, the vector valued function, giving the position vectors for those points on the curve, is of constant length, then you're always going to get that the tangent vector is perpendicular to the curve itself, or the position vector of the point on the curve itself. All right, so you always get the picture that looks like this. Let's see why that is the case. Okay, so let's prove this in general. Here's our proof. So we've got a vector valued function, r of t. We know it's of constant length. So that means if I dot it with itself, this is going to be constant. So that's some constant. Because the dot product of the vector with itself is the square of its length. So if it's of constant length, then it's some constant. In this case, it would be the square of that constant, but that's still a constant. Okay, so we've got that r dot r is a constant. Now we can differentiate. And how do we differentiate a dot product? Well, that would be equal to the derivative of the right-hand side. The derivative of a constant is 0. So we've got the derivative of this dot product is 0. How do we differentiate a dot product? That's given by the dot product rule, which says that it's the derivative of the first, so r prime of t, dot the second, r of t, plus the first, r of t, dotted with the derivative of the second, r prime of t, that's equal to 0. And those, because of the commutativity of the dot product, r prime of t and r of t, we can dot them in either order. So this is really 2 times r prime of t dot r of t is equal to 0. Or in other words, r prime of t, I can divide both sides by 2 dot r of t is 0. But that means that r prime of t is perpendicular to r of t. And that's what we wanted to prove. Prove that the tangent vector is orthogonal to the position vector. And there it is. Tangent vector is r prime of t, position vector is r of t, and we've got that they're perpendicular to each other. So that's a nice result. It says if you've got a vector value function which has constant length, then when you differentiate it, you get a vector that's perpendicular to the position vector for the function itself. All right. Next, we're going to look at integrals. And the idea is because differentiation happened component by component, then integration is done component by component. It's just basically we do it in reverse. Instead of differentiation, we now can do an integration. And we do it component by component. So that's this first definition. So the integral from a to b of r of t dt is just the integrals of the individual components. Let's do an example where we use this. Suppose r of t is a function such that its derivative is given by t squared I hat plus cos t j hat plus e to the t k hat. And furthermore, r of 0 is I hat plus j hat plus k hat. So in other words, if we do this using our tuple notation, r prime of t is t squared cos t e to the t, and r of 0 is 1, 1, 1. We want to find r of t. So the first thing we notice is that in order to find r of t, we anti-differentiate. So we compute the antiderivative. So the antiderivative of t squared is 1/3 t cubed. The antiderivative of cos of t is sine of t. The antiderivative of e to the t is e to the t. But when we do an antidifferentiation, we always get that constant of integration out. But the constant of integration here would be a vector. We'd get a constant for each of these components, so we'd get this constant vector. Let's say C0, C1, and C2. So those are the individual constants we would have got for each of those pieces. And now what are C0, well maybe I don't even need to put the brackets around here because I'm just asking what are C0, C1, C2? Well, we use the fact that r of 0 is 1, 1, 1 to find the value of the constant of integration. And so what we'll do is we'll say, we know that r of t is 1/3 t cubed plus sine t plus e to the t. So r 0 is equal to 0, that's 1/3 0 cubed, plus sine of 0, e to the 0, e to the 0 is just 1, plus C0, C1, C2. So that's what r of 0 is, because this is r of t. So just plugging 0 into this, we get this expression. But that's supposed to be equal to 1, 1, 1. So now we just compare. I need 0 plus C0 to be 1, so that means C0 is equal to 1. I need 0 plus C1 to be 1, so C1 is equal to 1. And I need 1 plus C2 to be 1, so C2 has to be 0. And so that means, therefore, that r of t is 1/3 t cubed. And I'll leave a little bit of a space to fill in those constants here. So that's our antiderivative plus the constants of integration, which we now know specifically what they are. It's 1, 1, 0. So we get a plus 1, and a 0. So there is our function, r of t, such that its derivative is what's given in the question. You can check that easily. The derivative is t squared, derivative of sine is cos of t, derivative of e to the t is e to the t. And when I plug 0 in, I get the value 1, 1, 1. All right. That's it for this example. Thanks for watching.